Okay, this is week 2. Okay, this is week 2, lesson 1. We're going to be looking at a new coordinate system today for the XY plane. It's called the polar coordinate system. And so let's just remember with the Cartesian coordinate system, what we do is we select a point in our plane, and we call this point the origin. And then we choose a line, usually it's a horizontal line, through that point. We call that our y-axis. And then we choose a line perpendicular, so this is at a right angle to the x-axis, passing through our selected point, the origin, and we call this the y-axis. And then if I have a point, say P, in my plane, what I can do is I can assign an ordered pair of values to P, and that ordered pair of values represents the location of P uniquely. And what we do is we measure the distance of the point P from the y-axis. So this is the distance we're looking at. Maybe I'll do it like that. And I'm going to call this x. And this is directed. So if P lies to the right of the y-axis, x is positive. If P lies to the left of the y-axis, x is negative. Okay? And then we look at the distance of the point P from the x-axis, and we call this y. So y is the distance between P and the x-axis. And then we write down the ordered pair where the x value goes first, and then the y value, we write that down, and that gives us the location of the point P. These are called the Cartesian coordinates. So x comma y in this case, these are the Cartesian coordinates of the point P. Where is that? Here we go. So now what we want to do is we want to look at a completely different coordinate system, and it's this. So again, what I do is I choose a point P, and here I have an x-axis. Okay, and suppose I have a point P in the plane. What I'm going to do is I'm going to measure the distance between P and the origin. Okay, so this point here, again, this is my origin. And I'm going to measure this distance, and I'm going to call this R. Okay, and then I'm going to look at the angle formed by the line connecting, by this line here, connecting P with the origin. I guess we'll make it a bright color. So I'm going to look at the angle between the x-axis and the radial line that connects P with the origin. And I'm going to call this angle theta. And here I'm measuring theta in radians. Now, here's the thing. This angle theta is being measured from the x-axis to the point P. In other words, we're measuring it in the counterclockwise direction. So whenever theta happens to be positive, we know that we've moved through theta radians in the counterclockwise direction from the x-axis. So let's look at an example. Let's look at something like this. Suppose I do this. We'll call this, let's see, what should I do? Let's look here. So this is 2 units. This is my x-axis. I'm going to call this my y-axis. So I have a Cartesian coordinate system. And I'm going to look at a point up here, P. So this point P in the Cartesian coordinate system has the coordinates 2, 2. Okay. So this is 2, and this is 2. And this distance here is going to be the square root of 4 plus 4, which is equal to the square root of 8. Okay? So now, what I want to do is I want to find the polar coordinates. Find the polar coordinates of P. Okay, well, what do we know? Those polar coordinates are represented by the distance from between P and the origin, which we know is the square root of 8. So this is r, and I'm going to call that the square root of 8. And then I have to find theta. And theta in this case is going to be this angle between the radial line connecting P and the origin and the x-axis. And because this is an isosceles triangle, and it's a right angle here, we know that theta is equal to pi over 4. Okay, so pi over 4. So the coordinates, the polar coordinates, of P are just given by the square root of 8 and pi divided by 4. Okay, so that's easy enough. But there's more to this. Number one, when I measure this angle here between the x-axis and this radial line, I could actually swing around a couple of times and come back here. So now what I'm looking at here is an angle theta equal to 4 pi plus pi over 4. So another polar coordinate representation of P is the square root of 8, comma, pi over 4 plus 4 pi. Okay? I could go around this thing many times, as many times as I wanted. So I could keep on spiraling around here and then come back here like that. And if I measure that angle, that's going to give me an angle theta, which measures the angle between the x-axis and our radial line. So in point of fact, the polar coordinates of the point P have the form the square root of 8, comma, pi over 4, plus n times 2 pi. Okay? Now think about that. Not only that, let's draw this again. I could do this. So here's my point P. And I could take and I could measure the angle this way. Oh. So now I'm measuring my angle theta. It's still, here's my x-axis. Here's the radial line. But since I'm measuring in the clockwise direction, so here we're moving in the clockwise direction to measure this angle, that angle is going to be negative. So this angle is in the clockwise direction. And so it's negative. And in point of fact, in this case here, theta is equal to, well, what is it going to be? It's going to be 7 pi, so it's minus 7 pi divided by 4. Okay, so another polar representation for this point is the square root of 8, comma, minus 7 pi divided by 4, which of course is what we get when n here happens to be -1. So the n here is any integer whatsoever, any integer. All right, so there are infinitely many polar coordinates for a given point in the plane. There's another thing that we want to do. Just an added complication, and that's this. So here's my point P again. Here's my distance between P and the origin. We know this is the square root of 8. But now, you know what I'm going to do? I'm going to put a minus sign here. Okay. So, if I look at this angle here is pi over 4. And I want to know, hey, what point is represented? What point is represented by minus the square root of 8, comma, pi over 4? So where is this? Well, what we're going to do is we're going to define this point to be this point down here. So this is the image of the point P about the origin. So here's Q. So this angle in here is just pi. All right. So the point Q has the polar coordinates minus the square root of 8, comma, pi over 4. All right. Minus the square root of 8, comma, pi over 4. This point Q also has the polar coordinates, the square root of 8, because that's the distance between Q and the origin. And then this angle is going to be pi over 4 plus pi. So if I measure this angle here, this is nothing more than pi over 4 plus pi, which is equal to 5 pi over 4. Okay? So, with this in mind, what is minus the square root of 8, comma, pi times 5 divided by 4? So what point is represented by this polar coordinate representation? Well, we know that the point Q has the polar coordinates, the square root of 8, comma, 5 pi over 4. If I make this negative, so if I make this negative, as we have sitting here, then this is just going to be, this is just going to represent the reflection of this point about the origin, which gives us the point P. So in polar coordinates, I have minus the square root of 8, comma, 5 pi divided by 4. This is another polar representation of the point P. So what we find is, unlike Cartesian coordinates, where when one specifies the coordinates of a point, those coordinates uniquely specify the point. Here, however, if I have a point, there are infinitely many polar representations for that point. What about the origin? What about this point here? Well, the distance of this point from the origin is, of course, 0. But what about the angle? The angle can be anything. Okay? So that point is very unique. All right, let's take a look at some problems. So let's suppose we have, I don't know, let's make it minus 2, comma, 7 pi over 6. So where is this? Okay, so these are our polar coordinates. And I want to find the location of this point. Well, what I'm going to do is this. I'm going to first find the point 2, comma, 7 pi over 6. So 7 pi over 6, where's that going to be? Well, pi over 6 is just this angle here. So this is pi over 6. And if I take and I add pi to it, let me get rid of that. So here's pi. So this is going to be 7 pi over 6. And now what I'm going to do is I'm going to move out 2 units from here. All right. So that brings me to this point here. Call this point Q. And then if I want the geometric representation, the location of the point whose polar coordinates are -2, comma, 7 pi over 6, all I have to do is reflect this point through the origin. So I get this point here. And this is the point P. So this has coordinates -2, 7 pi over 6. Not so bad. Not so bad. Well, there's another question that I can ask. Suppose that I have a point P whose polar coordinates, these are the polar coordinates, are R, I'm going to call it R, comma theta. So r happens to be this distance. And here I'm assuming that r is positive. And this angle in here, I'm going to call this theta. Okay? So what I want to know is, what are the Cartesian coordinates of P? So is there a way of finding the Cartesian coordinates of P? Well, what do I know? I know that if I can find this distance here, that's going to give me the y-coordinate of the point P, and if I can find this distance here, that's going to give me the x-coordinate of the point P. So x, this is a right triangle, and since we're dealing with a right triangle, we know that the length of this side adjacent to the angle theta is equal to r, the length of the hypotenuse of the right triangle, times the cosine of theta. And y is equal to r times the sine of theta. Okay. So what we can say is the following, that the point P has the Cartesian coordinates r times the cosine of theta and r times the sine of theta. Okay. So let's look at some problems associated with this. So let's say, find the rectangular coordinates for the following point. We have 6, comma, 2 pi divided by 3. 2 pi divided by 3. All right. So let's just draw this, kind of sketch it. Pi over 3 is equal to 60 degrees. So we're at a point P located in the second quadrant. This angle here happens to be 2 pi over 3. And the distance here happens to be 6. And now what I want to do is I want to find the Cartesian coordinates and I call them Cartesian coordinates. Other people call these the rectangular coordinates of the point P. Well, in this case, r is equal to 6. Theta is equal to 2 pi divided by 3. And so what I have is very simply the Cartesian coordinates are going to be given by 6 times the cosine of 2 pi over 3 and 6 times the sine of 2 pi over 3. Okay? And now I leave it to you to figure out the values of the cosine of 2 pi over 3 and the sine of 2 pi over 3. Okay? Suppose I give you the following point. I give you the point 1, comma, negative 2. So here's the point P, and these are the rectangular coordinates of P. Find the polar coordinates. Okay, I think we can do that. So I'm going to draw my rectangular coordinate system. This point is going to be 1 unit in the x direction and 2 units down So it's down here, we'll say. So here's my point P. So this is 1. This is -2. What do I have to do? Well, I have to find this length. Well, that's easy to do. All I'm going to do is the length of this side over here. The length of this side is the absolute value of the y-coordinate of the point P. So this is just going to be the absolute value of -2. That's 2. This is already positive. This is 1. So if I use the Pythagorean theorem, I find that the length of the hypotenuse, which I'm going to call r, is equal to the square root of 2 squared plus 1, and that's just the square root of 5. Okay. Now I have to find this angle here. And how do I do that? Well, that angle, I'm going to call it theta. So theta is equal to, well, let's do it this way. The tangent of theta is equal to what? Is equal to the opposite side over the adjacent side. So this is going to be -2 over 1. All right? And this angle, where this point P lies in the fourth quadrant. So this is tells me that theta is equal to the inverse tangent of -2. Okay? So theta is equal to the inverse tangent of -2. We need a calculator now. So let me see if I have a calculator around. Here we have one. Let's see. The mode is set to radians. So I'm going to punch in -2. I'm going to take the inverse tangent of that, and I get -1.107. So what we have for the point P here, that has the polar coordinates, the square root of 5, comma, -1.107. Okay. All right.